So, hello everyone. Today we will continue from the last slide where we discuss the overview of mass and material balance, and we discuss the law of conservation of mass, and with one example we demonstrated how it can be applied in the bioprocess to calculate the unknown quantity. Now, the learning goal for today's lecture is stoichiometry of cell growth and product formation. So, as if you remember the last class we discussed, for material and mass balance we require flow diagram, as well as we require the stoichiometric reaction. Stoichiometric equation. So, today we will see this stoichiometry for the cell growth as well as for the product formation. And in addition, when you are adding substrate which is being converted to the cells or the product, so we should be able to calculate the yield. So, what is yield coefficient, how it is defined, and how we can calculate the yields. And if you want to write any equation, you need to have the formula. So, we will just see what is the general formula for biomass which is used in the stoichiometric equation. So, as I told, stoichiometry relationships and material balance are needed in the bioprocess, and once these two things are there, stoichiometry relationship and material balance, we can apply the law of conservation of mass to determine the unknown quantities entering or leaving the bioprocess. So, if you remember the last example, what was known to us, the product and air supply was known to us. We calculated how much, what is the inlet amount required and what is the amount of off gases. So, when you want to start this applying this mass balance, this we require the stoichiometry of conversion, that how your substrate is converted to the biomass or how your substrate is converted to the product. And as I told, substrate is utilized for the cell growth, it is also utilized for the product formation, and it is also related with the generation of heat transfer. Typically in the bioprocess, cells are also considered as a product of reactions, and most of the time we do not refer as a cell, rather we refer cells whole as biomass. So, in the most of the conversations or the subsequent slides, typically we will be calling the biomass in the place of cells. So, as I told, what are the implications of this stoichiometry reactions? It will help us to formulate the media composition. By doing the mass balance, we should understand how much nutrients will be required for the biomass growth, how much nutrient will be required for the desired product formation. And once you are having this stoichiometry reaction or equation, and if you can balance it, then you should be able to calculate the theoretical yield and you should be able to compare with the actual or the experimental yield. So, as I told, this stoichiometry reaction is also needed to determine the heat transfer requirement. In addition, if you have the stoichiometry, one should be able to analyze the reaction kinetics. So, as I told, this mass and energy balance, this is a macroscopic view. It is independent of particular pathway or mechanism. So, as you know, from substrate to the product, there are n number of metabolic pathways are involved, but here in the material and mass balance we are considering as macroscopic point of view. So, this is a system which is having this inlet and outlet. So, what we are seeing, a substrate is converted to the cell is also a product of reaction, and of course, your metabolites is a product of reaction. So, one thumb rule we remember here that the free energy of substrate consumed should exceed the free energy of cells and metabolic products formed. So, the free energy of substrate should be higher than the free energy of products. It means total value of delta G, it should be negative, and which is must for any process to happen from thermodynamic point of view. So, what it says is delta G value should be negative, and then we of course we can calculate the yield factor that we will discuss in subsequent slides. So, yield it says Y x by S, x means biomass, S means substrate. So, how much biomass is synthesized, delta x, it will be what was the x in, x out minus x in divided by delta S, that will be S in minus S out. So, as we are having two different product, one was the biomass, other was the product. So, we should be able to define two different yield coefficient here. One is the Y x by S and second will be Y P by S. The x by S means delta x upon delta S, P by S means delta P, how much product is formed and how much substrate is consumed. So, the coefficient is dimensionless and has the unit of gram per gram. So, gram of biomass per gram of substrate, or here gram of product per gram of substrate. So, we can define yield coefficient in the same way. Even we can have this Y, you can define either a Y S by P or Y S by X, and if needed one should be able to calculate the Y even X by Y X by P. So, the definition remains same, the first term will be the numerator, second term will be denominator. So, for example, Y S by X will be delta S upon delta X. So, this is how the yield coefficient are defined, and the way it is defined one should be able to calculate the yield value. Now, when you proceed further, you have to consider the cell as a product, and typically we refer cell as X, and a cell may have different elements like it may have carbon, it may have hydrogen, it may have nitrogen, it may have oxygen and so on. So, if the weight fraction of element I is Wi, the minimum amount of element I in the substrate should be Wi into X. So, in this way we design the media. So, whatever is required for the substrate, the same amount it should be present in the media. Now, it is important to understand what are the constraints here on media formulation. The first is some substrate elements are released in the product, they are not assimilated in the cell material. So, when you are designing the media, you have to consider what is the product formation, and accordingly we have to consider the media formulation. Now, next is very important, what is the rate limiting as well as stoichiometric limitations. We will discuss in the next slide how we define this rate limiting and stoichiometric limiting. So, what is the stoichiometric limiting? The substrate completely exhausted first during the growth, that is called stoichiometrically limiting substrate. It means in the particular stoichiometric equation, this substrate will be completely exhausted. What is the growth limiting substrate? It says increase in the growth rate due to increase in the concentration of a particular medium component for the given strain and the at given environmental conditions. So, if your substrate, a particular substrate is able to increase the growth rate with increase in its concentration, that is called growth rate limiting substrate. And if your substrate which is completely exhausted first during the growth, that is called stoichiometric limiting substrate. Now, next is this specific nutrient may be limiting or specific product may also be inhibitory. So, that also one need to consider during the media formulation, that if it is limiting substrate or beyond a certain concentration, it may also have inhibiting effect. So, let us consider the substrate. Substrate is used for the assimilation, substrate is used for the growth energy, substrate is used for the maintenance energy. So, if I define this yield Yx by S is delta x upon delta S, and what is the delta S? Delta S is being used at three different places. One is assimilation, second assume as growth energy, third as a maintenance energy. So, we have to break this equation in such a way that this delta S will have three different components. So, one easy option is what we can do, we can write either 1 upon y x by s, or we can write y s upon x, and this will be equals to delta s upon. Now, we should be able to write in place of delta s, what you are going to write is delta s assimilation upon delta x plus delta s required for the growth on delta x plus delta s required for the maintenance on delta x. So, in this way it is also possible to have the bifurcation of the substrate for the different purpose. Now, before we proceed to stoichiometry equation, we need to know what is the general composition of biomass. So, here if you see this table, it includes the bacteria, yeast and fungi, and what is their composition? Carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur and S quantity, right. So, it is very interesting to see this carbon, hydrogen, nitrogen and oxygen, they constituents about carbon, hydrogen, nitrogen and oxygen, they constituents about 90 to 95% of cell mass. So, typically in the empirical formula just see, we consider these four elements C theta, H alpha, O beta and delta. Further it can be simplified if we consider for 1 mole of carbon, so you put theta is 1, it will be C, H alpha, O beta and delta. So, depending on as different microorganisms have different composition, so you just see their empirical formula is slightly different. So, for generalize, if we see the general equation for biomass, so we can consider this typical formula, it says C H 1.8, oxygen 0.5 and nitrogen 0.2. So, there will be two cases. In one case the empirical chemical formula for biomass will be given to you. Other option, if it is not given, one can assume this general formula, and based on this formula the molecular weight of biomass will be 24.6. So, this is the range of biomass. You can say this is starting from 22.5, it is going up to 25.5, rather 26.9, and when we say the general formula, the molecular weight is 24.6. It is also important to understand that in actual biomass the other elements are also present, like this phosphorus, sulfur and ash. So, typically what we do after calculating this biomass, we add 5 to 10% ash. So, that gives the actual biomass. So, if the biomass is 24.6, so we consider in addition it will have 5 to 10% ash. So, its biomolecular weight will slightly increase. Now, we will have a quick example here in the case of aerobic process. What we are going to have here, this is your substrate CHXOI. We are having aerobic process, oxygen, and it also require a nitrogen source. So, this we are adding a nitrogen source CHLOMNN. Now, what is the product? We are considering only biomass as a product, no other metabolite. Biomass sole product CH alpha, O beta and delta, D H2O and E CO2 is formed. So, the first step is you have to write this stoichiometry reaction, then you have to balance it. How to balance it? Let us say how many unknowns are there? A, B, C, D and E, and 5 unknowns here. A, B, C, D and E. So, we require 5 equations to solve this. The first we go for the, let us say, carbon balance. Carbon balance here is A in the inlet, output is 1 plus CO2E. We go for hydrogen balance. In the left side the hydrogen is AX plus Cl, and right side the hydrogen is alpha plus in the water 2D. We go for oxygen balance. So, here oxygen is AY plus 2B plus MC, this equals to oxygen here is the beta plus D plus 2E, and next we go for nitrogen balance, that becomes Cn equals to the delta. So, these become 1, 2, 3 and 4 equations, but there are 5 unknowns. So, we require one more equation. So, additional relationship we consider as a respiratory quotient RQ, and which is defined as moles of CO2 formed. What is the moles of CO2 formed? Is the E divided by moles of oxygen consumed. The moles of oxygen consumed is B. So, E upon B is the another relation. So, we got 1, 2, 3, 4 and 5 relations. If we can solve it, we should be able to get those 5 unknowns. So, let us consider one example here. The production of single cell protein from hexadecane is described by the following reaction. This is your substrate, or you can say carbon source. oxygen, nitrogen source. This is your product CO2 and H2O. So, how many unknowns are here? 1, 2, 3, 4 and 5 unknowns are there. So, we require 5 equations. RQ is given over here. So, we have to do this carbon balance, hydrogen balance, nitrogen balance, oxygen balance and then RQ. So, these will be the 5 equations. RQ is directly straightforward, 0.43 equals what is the CO2 formed, D to the oxygen consumed, D upon A. Let us go to the carbon balance. How much carbon is there left side? 16 equals how much carbon is there in the right side? C plus D. Hydrogen balance 34 plus 3B, that equals 1.66 C plus 2E. Nitrogen balance, this side nitrogen is B equals right side nitrogen is 0.20 C. Oxygen balance, this side oxygen is 2A equals 0.27 C plus 2D plus E. So, these are the 5 equation 1, 2, 3, 4, 5, and if you solve it you should be able to get those stoichiometric coefficient, and by solving this value will come out to be A as 12.48, B as 2.13, C as that D, A, B, C, C as 10.6, D as 5.37 and E will be equals to 11.36. So, after calculating this we can rewrite the final equation will be 12.5 is the value of A, 2.13 is value of B, 10.6 is the value of C, 5.4 is the value of D and 11.4 is the value of E. So, in this way we go for this material balance. So, now this is a stoichiometry reaction. Once this is there, it can be easy for us to go ahead with mass balance and determine the value of unknown streams. Now, it is important what we did here, we did hydrogen balance as well as the oxygen balance. But many times what happens in the bioprocess, we work with the aqueous environment and water is already present. So, in that case change in the concentration of water becomes not very significant. So, it has become very difficult to go ahead with the hydrogen and oxygen balance. So, for that we require some another equation, and that is called the electron balance. Which we will be discussing in the next lecture. So, what we summarize in this lecture is that how to go ahead with stoichiometry equations and what is its utility, starting from designing of media, considering what is the heat release, what will be the product formation. So, what we require for material balance is the stoichiometry relation as well as a flow diagram, and once these two things are there, we can apply the mass balance. But for the stoichiometry reactions, we have to write these equations. Then we have to calculate this stoichiometric coefficient that gives the clear this stoichiometric relation between substrate to the product. So, this was very simplified one. Considered this substrate is only converted into biomass, but in the actual you are going to have substrate is converted to biomass plus product, and this product can be a number of product P1, P2 and so on and so forth. Thank you so much. So, we will continue in the next class. Thank you so much.